Okay, let's get started. Last class we have stopped till this topic, the basic bistable element. You need to understand this because this is a fundamental to understand even the latches followed with flip-flops. Then we have master slave, SR, master slave, JK, and so on and so forth. Okay, try to understand this because this is simple inverter, not gate, which are cross coupled, as you are seeing here. Output of one is the input of other gate, as you can see here. This is the output of this particular gate is going as input to the other gate. This is called feedback, right? When you connect output back to the input, okay? Look at this. When you connect this, Y bar is the output here, and Y is the input here. Just for the namesake, we have labeled here Y and Y bar. And the first gate, you can see that there is X and X bar. Just for understanding purpose, we have labeled this as X and X bar. But later, once you become expert, you need not write all these conventions. Okay, so just to give an hint. And look at, there are two outputs here. What are the outputs labeled? Q is called normal output and Q bar is called inverted output. Okay, there are two outputs for the flip-flops. Okay, and depending upon the states of this, outputs of this, we can say whether flip-flop is or latch is storing 1 or 0. Okay, generally the conception what we have here is if Q is equal to 0 and Q bar is equal to 1, that's called reset state. If Q is equal to 1, I'm repeating once again, this anyway we are going through this in a brief. If Q is equal to 1 and Q bar is equal to 0 means, okay, it's called a set state. When set state, we are storing logic 1. In reset state, we are storing logic 0. That means this one particular circuit, it can store one bit of data, either 0 or 1. Look at the transistors inside this. How do you construct transistors, inverters based on transistors? Have you seen internal circuit of an inverter? Are you aware of internal circuit? It's made up of two transistors. If you prefer, BJT, with the help of one transistor, one resistor, you can make an inverter. Look at some circuit point of view. Okay, you may be curious that what is inside this symbol. Just this is a inverter symbol. Why we prepare symbols like this? Why we draw symbols like this? It's a standard conventions, Again and again, I cannot draw the circuit level, a diagram for you and explain that. That's why we develop standard symbols. These are called IEEE symbols. The symbols what you have seen for AND gate, NAND gate, NOR gate, all these are IEEE standard symbols. Otherwise, each person would have followed different symbol for NOT gate, AND gates, and so on. That's why IEEE has come out with a standard, and for NOT gate, you have to follow this. Buffer without bubble, if you write that, it becomes a buffer. It transmits just data with some delay. Okay, that's how the conventions are. Inside this, if you prefer to design with the help of MOSFETs, today's trend is CMOS. Okay, you will have one PMOS transistor and one NMOS transistor to build one NOT gate. Most probably you are going to develop this NOT gate, one NOT gate in your final year or pre-final year. 7th semester, I think in general, during that stage, you are capable of developing your own inverter with the help of transistors. We have a lab called VLSI. In that lab, you are going to design one inverter. You will see a lot of difficulties in designing one inverter. See, sitting at logic level, I may say that you are giving input 0 and I am getting complement of it. But how do you get that? Understand here? The circuit, the transistor, what I said, one is NMOS and other one is PMOS. It should accept logic levels. There are so many questions which will arise, when you develop an inverter. Generally, when we apply 0 volts, we say that output is 1 volt, 5 volts, which is logic 1. Question is now, what if I apply exactly 2.5 mid of logic 0 and 1? Anybody can guess what is the output of inverter? Or else I would try it any time conducting these experiments. When you give exactly threshold input level, what happens? You might have tested 0 volts and 5 volts, all logic gates. Or you might have tested with 0 and 1 generally. But my question is now, have you tested any logic gates with exactly mid of threshold? Then again, logic gates will go into confusions. Understand here? Exactly 2.5 volts you apply and see that. You can't expect what is the output. It's very tricky kind of things. Okay, so those things you will see, you will experiment when you go to the laboratory. Especially we use a tool called as a cadence tool to design these kind of inverters. Okay, this is a bistable, basic bistable element. This element will store logic 1 or logic 0, whichever you are interested. You can store that in this particular circuit. And look at, there is no special about this circuit, right? What is so special here? You have connected output of one to the input of other one. And only thing is, we have not given preference for the user to apply the inputs. We'll see that later, how to give choice for the user to apply the inputs. Just to show that how it works, we have written here. Okay. Here, let's start analyzing working this. Suppose if I assume that x is equal to 0 and y is equal to 1 to begin with. Okay. And also I should assume q and q bar. I cannot take same data right here. If I assume q as 0, I'm saying assuming. To begin with, I don't know what is the state. So I assume always start the operation understanding this thing, because these are the circuit which stores past history. Understand here? So assume that previously, before I start up the circuit, switch on the circuit, the state of q is 1 and q bar is 0. That's output state. I assume that first. And then I apply, say, x is, you can apply anything here. There is no combination like you must apply only 0, 0 or 0, 1 at the x and y. You can apply anything you want at x and y, but output you must assume either, if you assume q as 0, q bar has to be 1, or else if you assume q as 1, q bar has to be 0. Understand? You cannot assume same data, 0, 0 or 0, 1 at the output. In case if you are getting output as same 0, 0 or 1, 1 at the output, that state is called as a forbidden state, which we normally avoid in the flip-flop or latches. You are not supposed to push the flip-flop into the forbidden state. What is that forbidden state I'm calling? Both becoming 0, q and q bar, or both becoming logic 1. It is called forbidden state. Or sometimes even there is another state called as a race around condition, where output will keep on changing 0, 1, 0, 1. That is called toggle state. Understand? There is some state toggle state which we are not assured that what will happen after the end of the clock cycle. Even this circuit doesn't have any clock. Understand here? It's something like this. When I ask you to go from this wall, one side of the wall to other side of the wall, and I will tell you that I will give you just 1 minute time. And exactly at 1 minute time, can you guess where you are? It's very difficult, right? You may be at that side or this side, or you may be in between. We don't know that. That's a very important thing in toggle state. Because clock will not wait for everybody, right? Clock is periodic in nature. Whenever the rising edge comes, your toggle state starts. And when the falling edge comes, what should happen to the toggle? It should stop. But when toggle is ending, the falling edge appears, we don't know what state the toggle is there, toggle state conditions. Okay? And let's see this circuit. This circuit has got two cross-coupled NOT gates. This is what you are seeing here. And it has a feedback. Feedback means output we are connecting back to the input. That's the second point. And this is called bistable element. Bistable means output will be in one of the state, either one state or 0 state. Okay, that is called bistable. Bi means what? 2. Stable means states. Stable state, fixed states. Automatically it will not go from its own basis. It will not go for some other state. Stable means what? Unless you apply input, it will not change. You change the input, it goes to some other state. That's the convention. As usual, I have assumed x is equal to 0. When you assume x is equal to 0, q, you can see here, if I assume x is equal to 0, q is nothing but an x bar, which is equal to 1. And same one is now fed back to the input of the next NOT gate. And now y becomes what? 1. When y becomes 1, look at that q bar is what? Y bar of it. So q bar or y bar, which is equal to 0, which was assumed, right? Whatever you assume, it ends with the same state here. Okay, that's how this basic bistable element works. From this, see, every time we can't go for basic gates and implement it. Other operations are shown here. Please go through that. What happens when when q bar is equal to say 0? This is just the equations we arrived at. Q bar which is equal to x, which is equal to y bar, which is equal to 0, and q which is equal to x bar, which is equal to y. This is called one stable state. This condition q is equal to 1 is called a stable state, one stable state. It stores logic 1. And if you change x is equal to 1, the state may change from, look at here, we have 0, 1 state here. And when the moment you change the input, state changes from 1 and 0. This is called another stable state. That means you are seeing the same circuit in two states. In one state, output remains as Q is 1, Q bar is 0. That's one state. In another state, Q is 0 and Q bar is 1. This is another state. That means you are seeing the basic bistable element in two states, which is 0 and 1. Just observe any one of this, don't see simultaneously Q and Q bar. Observe any one of this. Let's stick to the Q. If you observe Q, look at here, Q remains 1 year. And look at in the second, when I change the input from x is equal to 0 to x is equal to 1, Q becomes 0 here. That's how the state, we have to assume that, okay? And always output should be complementary. You can't get same outputs. I told you already, if you're getting same outputs in the latch or flip-flop, that's called forbidden state, which that state must be avoided. And again, see, the output is off the way between logic 0 and logic 1 is called metastable state. This is very important definition. They may ask me in examination, what is metastable state? Metastable state, you don't see perfect 1, you don't see perfect 0. I told you, right? When you apply input exactly 2.5 volts, it's neither the 1 nor the 0. If you apply such a kind of state, can you expect what is the output? Output also, it will be in the intermediate. It will not go to 1 or it will not come to 0 also. It will be intermediate state. What is that state called? Metastable state. Understand here? So these very important definitions when you appear for interviews in companies like Intel or something like IC design companies, they will ask you these kind of questions. What is metastable state? There's so many other things you will come across in the sequential design. Whatever you are learning here, same thing is practiced in the industry also. Understand here? So you must become familiar, because these things, whatever we are learning here, even it's common for CS and IT branches also. They also learn similar subject, logic design or digital electronics. So once you get, these things are common for all the branches, let me tell you that, because without this, industry cannot do any designs, especially hardware designs. Okay. So process of storing 1 is called a setting state of a flip-flop. Okay, it's pre-setting state. Actually there is some mistakes in the spelling. Please be accept with that. And process of storing 0 is called resetting state. In this, Q is equal to 1 and Q is equal to 0. Which one you call as set state? Q is equal to 1 is called as a set state. Q is equal to 0 is called as reset state. That thing you must be familiar with that. Okay. And asynchronous inputs. So far what we have seen is basic element without input. X and Y just we have simply labeled it. But when you apply input, there can be two possibilities. One is synchronous input. What is synchronous input? If you remember last class, I gave an example to you. Like, you had to assume clock like a train. You remember that? Last class I given to you. And inputs are nothing but just like a passenger. I told you. Always analogies help you to remember for a long time. Understand? If train is like a clock, understand? Let's assume that train stops at periodically different stops. Okay. Generally in practice, train will the stops are not periodic. Okay. But you assume here it's a fast running train, fast moving train, and stops are periodic, just like our clock pulse. What is periodic with reference to clock pulse? If you stick to one particular rising edge, next rising edge will come after some time, right? And following the rising edges will come periodically. Understand here? It's called periodic wave, square wave. That is called as a clock. Clock is very important phenomenon. Let me tell you that. You need to dive a little deeper to understand more about the clock. Understand here? Timing analysis is very important. It is a broad topic in digital electronics. Normally, we don't teach that in colleges. Generally, when you go to the industry, they will teach you how to do timing analysis, static timing analysis. And you must be aware of, all these things. Clock, when it appears, when it disappears, when the rising edge comes, when the logic high comes, when the logic low comes, when the falling edge comes. All these things you must become familiar when you do some timing analysis. This is a hard cake nowadays. Let me tell you that if you are good in timing analysis without any, the written test and other things, directly you can get a job, provided you are familiar with some tools. Understand here? Getting job in this field is very easy. Let me tell you on that. It's not so difficult. Only thing is you must become expertise with the concepts, fundamentals. Later you must also attach with some tools. When I say timing analysis is very important from industry point of view, you can't learn timing analysis just by reading the book. Understand? You should take real circuits, say for example flip-flops, shift registers, counters, and do timing analysis on that. When I say timing analysis, you must see static timing analysis. Understand here? These are very important Look at many times you see Times of India or other newspapers, Wednesday's newspapers, you will see people are called for static timing analyst. Okay, just like software analyst, people will call, invite, industry will call software timing analyst. So hardware timing analyst, you must be familiar with the timing analysis. Yes, here and there, somewhere the fundamentals will touch related to timing analysis, but they separate the course for that. You can take up at different times, as an NPTEL course or some other course, and learn the timing analysis. Yes. So what I want to say is asynchronous inputs. Always you can't design a flip-flop or latch with asynchronous input. What is asynchronous input? Last class we discussed about synchronous and asynchronous, right? Synchronous means with reference to clock. You are applying input data with reference to clock. With reference to our analogy, the passenger is getting into the train with reference to what? When the train comes and stops. Understand here? What if the passenger misses the train? He will catch the next one. He can't catch same train, same time. Understand here? You connect that with synchronous. What is asynchronous? Just simply waiting. Train whether comes or not, we don't know. You simply wait. It's unexpected. Those circuits are called as asynchronous circuits. Generally, we don't do design of asynchronous circuits. Why? We have to have control, right? I want to know that when my data inputs from input side go to the output side with the help of clock, I must monitor each and everything with the help of a clock. Understand here? Entire look at this laptop, mobile phone, they operate with the help of clock only. If clock is not there, it's gone. Clock is like, in my opinion, it's like a heartbeat. If clock stops, everything stops. Either laptop or any electronic system you take, without clock, you can't design a system. That means 99.99% we do always synchronous kind of design. Again, I'm repeating, what is synchronous design? Your input data you're applying with reference to what? Clock. Understand here? Your data must be synchronous with the clock. Whenever the rising edge comes, exactly your data must be ready. Whenever the train comes, passengers must be ready. In fact, what we expect is to be accurate. That we expect passengers to be ready well in advance before that rising edge comes. You understand what I mean by that? Passengers cannot get the train coming and passenger getting. You can't have simultaneously both the things, right? Understand here? Whenever the train comes, passenger must be ready at least little amount of time prior to what? Rising edge comes. Understand? You can't expect D should be 0 or D should be 1 or JK should be 1 and 0 when the rising edge comes. You can't expect that. Prior to the rising edge coming in the clock, we expect that J and K, at least for some time, some duration before that rising edge coming, it must be 0 or 1. But also ensure that you must not change your data when the rising edge comes. Understand here? These are the timing, what I'm telling once again. We say setup time and hold time, right? What is the definition of setup time in flip-flop design? You must maintain input data constant prior to the rising edge. This is called setup time. You must maintain even data constant even after the rising edge passes. Hold time. These are all normal things, in the flip-flop design. Most of the times when we do design of flip-flop, we don't focus on these kind of things. We think that, anyway, a clock is there, data is applied, output will appear. Sometimes you get wrong kind of data if you don't follow these kind of things. Okay, from this slide, what we can conclude is now, we always do apply synchronous inputs, affect state of flip-flop when control or enable or clock is applied. I think some mistakes are, please be accept with that. Whenever you apply that, with reference to that, if you maintain synchronous, then it is called synchronous kind of circuit design. S is called set input. These are keywords which you should remember. R is called reset input. Okay. And even JK sometimes we say no. Okay. It's a Jack Kilby is a person who invented the integrated circuit. That's why we always name before who invents that JK. Okay. Almost all flip flops are named labeled with the inventors. Okay. Look at this truth table. This is a truth table for the previous element what I showed here. Look at this one element. For this is the truth table. Okay. S and R. You just go through this truth table. What happens here? 0, 0. What is that 0, 0? When you apply S is equal to 0 and R is equal to 0, what is Q and Q bar? Q plus is called next state. Plus means superscript, what you see is called next state. Presently, before you switch on, whatever state is there, that is Q and Q bar. You have seen in the latch also, right? Inverter base, that is called Q and Q bar. Q plus means after applying, the input, what will happen here? When you apply S and R as 0, 0, it remains Q plus will be Q plus bar, complement of the output will be Q bar itself. Okay, that's how the operates. And when you maintain S is equal to 0 and R is equal to 1, it maintains 0 and 1 same combination. 1 and 0 will have 1 and 0. This is what the state which I suggested you to avoid them. When you apply input S and R both as 1, 1, what will happen in the inverter? Whatever the data you assume here, output, both the outputs will go to the low. You just try that. I'll just go to the circuit, apply this combination and check, see what happens here. What is that we are assuming here, X and Y, or S and R, what we say? 1 and 1, you assume that, and you assume whatever the state here, and whether 0, 1 or 1 and 0, whatever you assume here, at some point of time, what happens, this both will go to 0. Or both will go to 1. That state is called as a forbidden state, which is not expected in case of latch or flip-flop. You must avoid that. Okay, so that's called as, that is explained in the truth table. But for when I go to the SR flip-flop, I will explain in detail what is that forbidden state. Any questions about this? Let's not worry too much. These are the fundamentals what we are discussing here. But when we go to the actual syllabus, we'll explain in detail what do you mean by unpredictable state or behavior state. But this particular circuit, when S is equal to 1 and R is equal to 1, it goes to the forbidden state. You can see that both it has become 0, 0, which we don't expect from the latch or flip-flop. Okay. And this is a RS latch, what we are saying here. This we call as a latch. There is a difference between latch and a flip-flop. Latch doesn't have any clock or enable signal. So this latch is built from the NOR gates, just like in previous. Why we are moving from NOT gate latch to this NOR gate latch? It's universal gate, that's number one, because we can't design latch or flip-flop with the help of basic gates. In fact, you must avoid basic gates only, I will tell you that, because today you see commercial ICs are manufactured from the universal gate point of view, not from basic gates point of view. Only for the beginners. Okay, if nobody is at least if you are first semester students, if you want to gain knowledge in digital electronics, you can start with basic gates. But once you become an advanced logic designer, you need not look at the basic gates. You always, for any logic realizations, you must depend on the universal gates like NAND, NOR. Understand? And sometimes you can use even special gates like XR and XNOR also for arithmetic operations especially. Okay, that's very important here. Okay, all right. This is a latch which is built from two NOR gates. You don't see any difference, but only thing is in place of NOT gate, what you're observing here is a NOR gate. And also previously, we see for the same feedback itself, you are supposed to provide the input. But now here we have dedicated input, which we call as a reset input here, and is a set input. Output of this NOR gate comes as input here, and again this is controlling this, because this output comes here. This output is controlling this input, and this input is coming from this output here. That means one is holding the other one, right? That's how we can see this is a cross-coupled. This circuit is called as a cross-coupled. Same thing you can also build from basic gates. You can interpret this, not build, what I'm saying. So you have your NOR gate followed by a NOT gate, which is same as this. Both are equivalent, of course. And this symbolic representation of this RS latch, or whatever you call SR latch or RS latch. This is a latch basically. The reason is we don't have any control element for this. You apply data, you get the output. If you don't apply data, you don't get the output. It is more or less, it looks like a combinational circuit. But the topic is sequential circuit. Understand here? So we'll see how to arrive at a sequential circuit from the combinational perspective. This is, in fact, it is a combination circuit only. Why I'm saying this is combinational? What is our definition for combinational network? Output depends on input. So here Q and Q bar output depends on the input. Understand? You change the input, output changes. Because there is some delay here, 2 gate, one level delay here from input to output. If I assume that 10 nanoseconds delay for each one of this gate here, understand, after 10 nanosecond delay, whatever the input you apply, depending upon that, the results will be produced. Understand here? It's very simple combinational logic circuit here. Okay. And I have explained all combinations here. I suggest you to go through each of these combinations. Okay. In some circuits, some slides I have just worked out on the circuit itself to make you to understand very well. Look at this first one here. Q is equal to 0. First, let's assume that what input we are applying, R0 and S0. And I'm assuming that Q is 0, Q bar is 1. And what we expect from output, you can just guess here. What is our input assumption? Both are 0, 0. R and S are 0, 0. Q is 1. Q bar is 0. Okay. So now, what is the state next state you expect here? Look at this. It is 0, 1. Are you able to get it? Are you able to understand this? I'll just go to the circuit once again. Look at here. What I'm trying to say is 0, 0. Write one side truth table of an OR gate. What is NOR gate truth table of it once? You all forget. When both are 0, it's 1. Rest all. So one thing, what is common in the entire NOR gate truth table if you observe it? If any one of the input is 1, output becomes 0. That's what simple logic. Don't look at too much about the NOR gate. If any one of the input is 1, output becomes 0. Understand? Let's not look at the special one here. Now look at here, as what I assume is both are 0, 0. Right? And look at this, what I assume here is, I don't have a chart here, I have showed here. Everyone can get a chart here. Here I can't write anything. So here 0, let's assume this 1 and 0 here. You can assume anything here. There's not compulsory that you must assume always 1 and 0. You can also assume what? 0 and 1 here. Q has 0 and Q bar is 1. For the time being, let me assume this has 1 and this has 0. Already you know what here? Both are 0, 0. This is 1. 1 comes here. 1 and 0. What happens? It remains 0. The 0 goes here. 0 and 0. It is 1. Understand? That means whatever I assume, it's gaining same thing, right? You understand this for here? This inputs are fixed. Both are 0, 0. And this keeps changing. I assume here as 1 and 0. 1 comes here. 1, 0 is nothing but 1. And this 1 goes here. 1, 0. This 1, 0. 1, 0 will change to 1 here. 1 comes here. 1 and 0 again here. This changes to what? It is 0, right? Check. Please can we get one check? I'll just explain this if you have any confusions over that. Thank you. Just look at this. Same circuit I am drawing here. Yes. Observe here. This is the Q which you are labeled. This is the Q bar. I've taken this as 0. This as 1. Don't make noise, please listen here. 0, 0. What is our NOR gate truth table says? For 0, 0. Let us say X and Y. This is 1. This is output Y. Let us say this is A, B and Y. And for 0, 1, 1, 0, 1, 1, for all conditions, it remains as 0. Now see, this 1 comes here, 0, 1, which is nothing but 0, 0 goes here, 0, 0, this is 1, 1 again comes here, 1, 0 remains as 0. That means, even though I started with 0, 0 as input, whatever you assume here, to begin with I assumed with 1 and 0, the state remains. Even after a few hours of time, if you observe, the state remains as 1 and 0 only. Whatever you assumed in the beginning, that state will be continued. Can we call this as a no change state? Our output remains in the what? Previous state. Okay, that's a state what we are observing here for this. And look at other combinations also. What will happen if I change the inputs? Here I started with 0 and 0. What happens if I assume 0 and 1? This state definitely as it is. Now see here, 0. And here I assume this, this 0 comes, let us start with the first bottom one here, you can see here. I have taken 1 here, 1 and 1. It is 0, 0 goes here, 0 and 0. It is 1, 1 comes here, and then again 1 and 1 remains 0. That means this remains as, if you want, you can write this state as, this remains as 1, that is the next state. This is next state, and this remains as what? 0. This is called set state. Understand it? And let's assume reverse now. I have taken R is equal to 0 and S is equal to 1. What if I assume R is equal to 1 and S is equal to 0. And here let me assume that both are 1 and 0 now. Now let us see, analyze this thing here. The 1 comes here, 1 and 0. It is 0. 0 goes here, 0 and 1. It is 0. This changes to what? 0, and this changes to 0. Now let us see here, the 0 comes here. This will change to again 0. 0 and 0 is nothing but this changes to what? 1. The 1 comes here, 1 and 1. It's 0. That means it remains at 0. Now you see here 0 again coming here. Remains as 1 only. Understand? This is going to be the stable state now.
In the beginning, when we are starting to find like mapping the 0 and 1, so always should we start from the lower gate?
Need not be. You need not start with lower gate. But you know, for simplicity, I have started with lower gate. You can also start with upper gate. But what is important here is, don't look at only one particular state here, conclude that output itself is that state. You would always see for 2-3 cycles. Just like here you see, we started with what? 1 and 0. To arrive at stable state, I took almost the 3 states, right? I progressed to 3 states. Then only I got the stable state here. Understand here? So that means you need not to come to the conclusion that when you apply an input here, at least you should analyze for 3 states. You will get to know what is stable state. And now you will see that 0 and 1. Even you wait for how long you want, you can wait here, but still the state remains same. 0 and 1 is the final state. What is this 0 and 1 called? It is called reset state. And for what it has reset? Look at here, when you make R as 1. When you make R is equal to 0, S is equal to 1, it was a set state. When you make R is equal to 1, S is equal to 0, it is called reset state. Let's now analyze what will happen if I make both as 1, 1. Let's remove all these things, just look at this, how I analyze. Now look at this. I started initially with 1 and 0. I made both as 1 and 1. Now this here, let us start with this. 1 comes here, 1 and 1. Next state is 0. I would like to write here arrow mark, next state is 0. The 0 comes over here, 1 and 0. This is what 1 and 0 is, 0. 0. The 0 comes here, 0 and 1. It is 0 only. Okay? And 0 comes here, 0 and 1. Now see what is happening here? We didn't expect this one, right? It's called forbidden state. Both outputs are going 0, 0. It's called forbidden state. That means this particular latch, NOR based RS latch, goes to the forbidden state when you apply both as 1 and 1. This will persist even if you go for, till you go for what is that gate, JK flip flop, till the forbidden state will persist. Understood these things? Any questions for you to analyze this? When it comes to the topic, I have just deliberated a little bit detail, but this is only fundamentals. I don't want to spend too much time on this. Therefore, I have quickly given my analysis in the form of a table here. Just go through this. Whatever I explained here, it's there in the form of in the slide. You can go through that. Okay. Just is it same? Look at this. 0, 0, no change. We already explained that. 1, 0. 1, 0 means it is reset state. Okay, R is equal to 0, S is equal to 1 is called set state. Lastly, what we have is both 1, 1. You don't see complementary output, but what we expect from latch is complementary output. It's called forbidden state. This state must be avoided. And we don't know, sometimes it may enter into metastable state also. Metastable, there is no proper output. That's called metastable state. Alright, now let us come to another latch called SR latch. You should not call this SR latch, simply it is S bar R bar latch. What is the difference between previous latch, what we have discussed, NOR based, to the present one? We changed gate, right? Instead of having NOR gate, we preferred here what? NAND based. And there is a reason here why we have gone for this S bar R bar latch. Reason is I want to build, SR flip flop. For SR flip flop, which is NAND based, this serves as a part of that. Understand here? So if you understand this very well, I hope you can do that, because previously you analyzed NOR based latch. On similar basis, you can also analyze what? NAND based latch. Understand here? Look at here the inputs. Here in this case, what happens when both are 0, 0? What is it? Forbidden state. Previously what you got? Forbidden state? When both has 1, 1. But here it is totally reversed. You are getting forbidden state even in the circuit also, but condition is now for the input both as 0, 0. Understand here? And you see the no change state where you are getting for this. No change state is the last one here. 1, 1, you are getting the no change state here, was 0, 1. Whatever you assume, it remains as 0 and 1 only. And 0, 1, you get 1 and 0, opposite of it. And 1, 0, you get 0, 1. You just analyze this. I have given all 4 cases here. Case 1 is discussed here with the NAND truth table here. Just go through this. Okay. The way I have done here just now, I have explained the same thing here. S is equal to 0, R is equal to 0, both are 0, 0. And I have assumed as 0 and 1. And look at here, 0 comes over here. 0, 0 is nothing but 1. Output becomes 1 here. Next state is 1. And 1 goes here. 0, 1 is again 1. And 1 again comes here. And look at here 1. That means you observe here output remains both as 1. This is called forbidden state. Likewise, we analyzed all 4 cases. Okay, go through this. Case number 3, 4, all these things has been analyzed. Last case for both 1, 1, S bar is equal to 1, R bar is equal to 1, it enters into the previous state. Whatever the data you start with, begin with for analysis, the same data will be retained even after the next state. Okay. Little bit confusion you may have. I am saying always state, next state, state, next state, because the topic is like that. When I say state means before applying the input, what is the condition? That is called as a state. Next state means after applying input and after the few clock cycles you have to wait. If it is a flip-flop, then you will see what is the next state. Let's come to the gated SR latch. This is the first step to understand the master-slave JK flip-flop. SR latch, gated SR latch. Look at this, try to understand this better. And look at, as I told you, previous circuit, what we were discussing, the part of the circuit, right? Look at this part. What is this? S bar, R bar latch. And this is what? Gated input. Why we call gated input? Because we take one of the input of this gate and connect it to the enable. Previously, whatever circuits we have discussed, they are not real sequential circuits. They are all combinational circuits. Why it is combinational? Because you don't have control. Have you anywhere seen the control in the previous circuits? We started with NOT gate based latches, NOR gate based latches. We have seen NAND gate based latches. The moment you apply input, you get the output. Understand here? If you don't apply the input, you don't get the output. But look at this circuit is now, we have now control. What is the control? Enable. Now this plays a very important role. Understand here? See, in any electronic circuit, you should have a control. Otherwise, circuit or device becomes useless. Look at transistor, you have 3 terminals. Diode, 2 terminals, useless. We don't have control over diode. Only input comes, output appears. Understand it? Always we should have a 3 terminal devices. Look at all devices which are recently invented or fabricated are all 3 terminal devices. We should have one control always. Look at transistor, which is controlling a transistor? BJT? Base. MOSFET? Gate. Without gate you can't operate, right? How much current has to flow from input side to the output side? Controlled by what? Gate. With reference to BJT, how much current should flow from emitter to the collector? Controlled by base. That means you have some control, right? Otherwise you can't operate. Likewise, even in the circuit also, what data input you apply, whether it has to go to the output or not, that you can decide here. How can you decide? As long as you maintain enable as C, what happens in the circuit? Here I started with enable is equal to 1. Just look at this. This enable is equal to 1. Let us analyze truth table of this particular circuit. Already you are aware of this part. And now analyzing entire circuit becomes very easier. First case you can see here S is equal to 0, R is equal to 0 and C is equal to 1. This is our control, as I told you. If you want to disable this, if you want to make output as uncontrolled with your inputs, then make it as C as 0. C 0 means it will not operate. C is equal to 1 means it will operate. That's how you can think. Later on, I will make this C as a clock signal. Understand it? Here I have started with making C as 1. And look at this are 1. Was 0, 0. And Q is I assumed as 0 and 1. Q of bar as 1, Q as 0. Now see what happens here now. 0, 0. Clock is 1. Now how the NAND gate operates? Truth table also we have shown just how NAND gate operates here. If any one of the input is 0, what will happen to the output of a NAND gate? It once. When both inputs are 1, then only output of an AND gate is. So that's a special here in AND gate. Understand? You should always ensure that when both inputs are 1, then only output becomes 0. If any one of the input is 0, then output becomes logic 1. That's how the NAND gate works. Look at here now, 0 and 1. One of the input is 1 here. 0 and 1. Obviously output will be 1. Understand? 0 and 1. Output will be 1. Let us see what happens to the next part of the circuit. So 1 and 1 is there. And here I assumed 0 and 1 to begin with. And 0 comes over here. 1 and 0. What will be the next state? 1. And this 1 comes over here. 1 and 1. 0. 0 comes over here. This state remains, right? You keep on analyzing again and again and again. Will it change apart from anything else from 0 and 1? It doesn't change, right? That means I made C as 1, S is 0, R is 0. What state it has entered? 0 and 1 remains same as 0 and 1 only, right? That means the SR flip-flop remains in the previous state. This is called previous state. Next state is nothing but 0 and 1. Next state, Q plus is next state. Okay, that means I can say that for S is equal to 0, R is equal to 0, this SR flip-flop remains in the previous state. Look at here, how we get previous state? Q plus is equal to Q. Q plus bar is equal to Q bar. That is called a previous state. Understood this? Let's go to the next combination now.
So for S1 R1 latch, unpredictable state was for 0, 0. Here it's for 1, 1.
It changes, we have control input, right? NAND gate. That changes overall scenario now. You stick to this now, and the second part, when it comes to second part, you look at the previous circuit what we have discussed. Understand here? So we are connecting, only thing is we are adding additional control here, that's all, nothing else this point. For the previous circuit. Okay. So you already know truth table for that, and you are adding control for this, we are developing overall truth table now. And now based on this, you see that when it will go to the forbidden state. For first condition we have seen already, it goes to the no change state for 0, 0 condition. As long as clock is or enable is 1. Let us see that for all these things I made enable as 1. Only for last state you can see here, when enable is equal to 0, whatever the input you apply here, it goes to previous state. Understand here? That you can also analyze. You assume one state. I've done that in the material. You can go through that later on. Let's go to the case 2. Quickly you analyze. I don't want to spend time on that. Just like I did analysis quickly, what happens? Okay, you analyze this and ensure that whether the output state is correct or not. S0, R1, Q0, Q bar, 0 and 1, C is 1. Look at this, substitute now. 0, 1, 0, 1, 1, 1, 1, 0, 1 comes here, 0 comes here. You already know truth table for this. For 1 and 0, what is the output? 0 and 1, just reverse. Understand here, the next state is going to be 0 and 1 because already I know the truth table for this. Understand here. Now look at here, for 0 and 1, what I am getting is 0 and 1 only. Okay? So next state is going to be 0 and 1. Look at the next one, case 3. Case 3 is now, I am making S1 R0. This assumption remains same for all the cases. C remains 1 for all the cases except last one. Now just analyze this now, what happens? S1 R0, C remains 1, 1 and 1, 0, 1 and 0 is 1. And look at here now, I assumed with 0 and 1. Here I have stopped what input it is coming. Now we look at this because I want to see what is the present state. So 0 and 1 is the assumed present state. 0 comes over here, already 1 is there. 0 and 1 gives you the 1. 1 goes here, 1 and 0 gives you the 1. And again 1 comes here, 1 is there already. So 1 and 1 remains as 0. And look at here, the 0 goes over there, and 0 and 0 remains as 1. So that means stable state is 1 and 0. Okay? Understood? Even if you analyze for the half an hour or 1 hour, the state remains same, 1 and 0. So what I can conclude now is, for this particular input, this assumption, clock is 1, the next state is going to be Q plus is equal to 1, Q plus bar is equal to 0. Understood this thing? Alright, go through the next cases, few cases. Case 4 and case 5. Even don't care case also considered. You see now forbidden state, when both S and R, if you maintain as a 1, it goes to forbidden state. Remember, NAND latch, when it goes to forbidden state, if you look at NAND latch alone, for 0, 0, it goes to forbidden state. But now look at here, for 1, 1, it goes to forbidden state. If you already designed SR flip-flop with enable, with gated inputs, For this particular condition, it goes to the, for one condition, it goes to the forbidden state. You must avoid this state. Understand? In real design, circuit design, when you want to use this as a storage element, you must ensure that the input data, whatever it's coming, will not go with 1 and 1. Understand? What happens sometimes, when you design this wrong flip-flop and make this circuit as a part of your big design, what may happen when circuit encounters this particular case? Any guesses? Nobody, God only should guess what is the output. Suppose that my question is now, you have designed a complex circuit. In that complex circuit, let us assume that this is one part, one flip-flop is a part of that circuit. Unknowingly, if data comes as 1 and 1 for both S and R, clock, you can't control that. I told you clock is like a train, you can't control that. It keeps coming every now and then, after every time. You can't control that. But assume that your data input itself is 1 and 1, unknowingly it comes. What will happen? It will affect even other part of the circuits also, right? Because you can't guess this 1 and 1. You might have designed other part of the circuit assuming synchronous and other part of the circuit works without going to the forbidden state. But now you see this element has gone to the forbidden state. It's very difficult to bring back to the normal state. Understand here? That's why this is a job of the digital designers. When they go to the industry, they must identify these things. Whenever the spike appears, their eye will catch on that. Their duty is to observe the waveforms. Every waveform they keep on observing. And whenever there's small spikes coming, just like, in heart beats, in heart point of it is safe when spike comes. If it is flat, the person is dead. But here, spike comes, sudden spike, then there is some problem in the circuit. Okay. Sudden spikes are not, you should not see in the digital circuits output. Okay, all right, this is what, any questions about this? So far what we discussed is flip-flop, gated. If you understood this, then definitely building a gated D-latch or D flip-flop, what we call, now onwards I should call it a flip-flop because I have a control now. Previously I don't have a control. This is called D flip-flop. Understood D flip-flop? Now I need not expand to D flip-flop because I already explained you what SR flip-flop. What I did here now? To avoid forbidden state, I clubbed both the inputs and connected through what? Now you don't have a choice to apply what? Forbidden state. This will not go to forbidden state now. And you see the truth table? Do you see anywhere forbidden state here? Now this is one of the most widely used flip-flop in the digital design. Understand? You ask anybody, they will design only D flip-flop, not even T flip-flop also. Understand here? That means you'll be close to the industry if you become familiar in designing D flip-flop, not even JK, not even master slave. Nobody cares for that. All timing analysis you should do on this. Okay? They will not ask you, write the logic, get a level diagram for D latch or D flip-flop and show the explain the output. Those kind of questions, it'll end up at the academic level only. Questions will be a little bit bigger. How do you do the static timing analysis on the D flip-flop? How do you, there are certain properties, when it comes to timing. Example is, you must maintain minimum pulse width, clock pulse width. Otherwise, it leads to error. You must have proper rise time. You must have proper fall time. Understand? In the design of a synchronous sequential circuits. If you don't maintain all these things, you're going to end with a error. I told you, I'm not dealt more details on that. For your information, to have basic knowledge, I suggested you a few things. Please go through this from the textbook. You need to understand propagation delay, pulse width, setup time, hold time, all these things when it comes to the flip-flop. Okay, this is not part of our syllabus. That's why I mentioned here as just a topics. Please go through that to become more expertise in the flip-flops. Okay, in timing analysis especially. Now let's come to the topic. So far, what we discussed is just a preview. Okay, hopefully you understood. I hope you understood the basic latch, how it works, flip-flop, how it works. Industry point of view, they will ask you difference between latch and a flip-flop. What is your answer for that? Flip-flop as clock or enable. Latch doesn't have any control. It doesn't have any enable. Understand? And what is the problem with that? If you don't have a clock, any input can come and change the output. It looks like more or less like a combinational circuit. It's not truly sequential circuit. Any noise coming, we can't expect always input to be accurate, right? Noise also can come. Understand here? So we are teaching here something, disturbance happened no there. Did we expect that? Noise, unwanted things will come. Even same thing happens in the circuit also. Understand here? Your latch will penetrate, propagate everything to the output. It treat everything coming at the S and R or J and K. All are useful inputs. Understand? That should not happen. For that we should have a control. What is that control? Enable. Whenever noise comes, I must make enable as 0. When there is no noise, when I have a proper inputs, I must make enable as 1. When enable is 1, data are sampled and passed through the gates. That's how the things works. Let's move on to the syllabus. Master slave flip-flop, very important. Master and slave. Understand this concept, I don't know how the idea has been conceptualized, but it is very important flip-flop. There's a 2 flip-flops. Right now what we have discussed is just 1 flip-flop. In master and slave, you will see 2 such flip-flops. One is called as a master flip-flop, other one is called as slave flip-flop. But whatever the master gives, slave should accept it. Slave cannot give back anything to the master. Understand? The concept is something like that. These are basics. Please go through that. There are 2 sections: master section, slave section. And at one edge or one level, I mean, when enable is equal to 1, you may get some information will be, the estimated, and some information be estimated, and next level, next enable, next time when you make enable, that information will be transmitted. Understand here? So this is the circuit for master slave JK flip flop, master slave SR flip flop, not JK. Look at the circuit basic. As I told you now, we now go from from gate level to symbolic representation. Previously the SR flip flop, what we have discussed, now that I have made the form of a box here. Okay, and working principle, everything remains same. That means when you keep building systems, when you go for higher level, you have to make a boxes, because we can't go and explain every time gate level circuit. And inside this, you should assume that there is a gated SR flip flop with enable and all such kind of things. And outside, when you look at, there is a S, R, and C. And output, there's a Q and a Q bar here. There's a bubble here. That's why we showed as Q. Like this, there are 2 flip flops are there, SR flip flops. One I have called as master, other one I have called as slave. For the first one, we apply a clock or enable directly, and for second one, it goes through the inverter. Simultaneously, both master and slave will not become enabled. If this is enabled master, it keeps capturing data from the input, and when slave becomes enabled, the master will be disabled. At that time, whatever the master computed data that will be given to the slave, this will start computing data given by the master and start producing the outputs. This is just like a cascade kind of arrangement, what we have seen previously in adder and even the comparator circuits. Understood the construction part? Any questions about construction? Yes. Yes, you're right, because it needs 2 clock cycles for the data to appear at the output. Okay, we can minimize that, that's not an issue, but later we'll see how to optimize that. Few things you need to understand. When the master enables, master disables, this flip-flop action during the control signal, look at here. First part we given a clock, enable, and second part you can see here at T1, what happens now here? Clock is 0, enable is 0. For enable 0, who is enabling? Slave has enabled, master is disabled. Look at here, from T1 to T2 we are not doing anything. Still master has been disabled, but here you can see that at T1 this has been disabled. Okay, slave has been disabled. From T1 to T2, both have been disabled here. This is called again forbidden state. We'll see that how to resolve this issue. But look at here T2. I want only to explain to understand you what is happening at T1. T1, I only will say slave is enabled. Slave, has enabled till T1. From T2 onwards, master enables. From T3 onwards, master disabled. Slave enabled after T4. Understood these things? Don't worry too much about these timing diagrams. And we have some conventions like low to high is called rising edge, leading edge, positive edge, high to low is called falling edge or trailing edge or positive. I mean, this is negative edge. These all things I have labeled here itself. Okay, this is a clock pulse. I only suggest you to remember this. At T1, what is happening? I will expand that. T2, what is happening? T3, T4. Only those things you remember that. Don't go more details. And I showed the flip-flops output in the form of a truth table. Just go through this. S and R 0, 0 is a clock pulse. It remains in previous no change state. 0, 1, 0, 1, 1, 0, 1, 0. It's outputs. 1, 1, undefined state we have. And finally, for the don't care conditions, you can see when label is control is 0 for don't care, it goes to the no change state again. We'll continue with this and look at even a symbolic representation of master slave JK flip flop. And this arrow marks here, the bent, the symbol here indicates it's a postpone indicator. And this is the, for timing diagram, we'll take up in the next class, because to understand this entire master slave JK flip flop, one need to understand this timing diagram. To understand this, I will just write the timing instance in the next class. Probably I think we can take up this in the next class and continue with JK master slave flip flops. Any questions before we end up here?